A more significant improvement in noise levels can be obtained by ensuring that adjacent propeller tips are separated by some optimum angle to prevent noisy interaction between them. This interaction is at a maximum when the propeller blade tips are opposite to each other, as is shown here. The synchronization system often also incorporates a synchrophasing feature that allows the operator to phase the propellers. Phasing is a means of adjusting the position of the blades on one propeller in relation to the blades of the one adjacent to it. The ability to phase can allow the operator to move much of the propeller vibration to unoccupied sections of the aircraft, thereby reducing the annoying beat of the propellers and providing additional comfort to the passengers. The systems of some aircraft provide the pilot with a means of manually fine-tuning this angle to obtain the quietest result. The more powerful an aircraft engine becomes, the larger must be its propeller if it's to absorb the torque output of that engine. Unfortunately, if the propeller diameter is increased as a way of increasing the size of the propeller, and the engine rotates at the same speed as it did previously, the propeller blade tips would be moving at sonic or even supersonic speed. This is very inefficient as well as being noisy and potentially damaging to the blades. So, if we have to use a large diameter propeller and yet maintain its RPM to a level that will not allow the tip speed to exceed that of the speed of sound, the propeller drive speed must be reduced to a more suitable level by a reduction gear placed in the driveline between the engine and the propeller shaft, as is this example of a Pratt & Whitney R4360 engine, which is shown as a cutaway. The parallel spur gear type of reduction gear, whilst being mechanically simple and relatively cheap to produce, takes up a lot of room at the front of the engine. This is because the axes of the gears are parallel. This system of reduction gear has been utilized mostly on V-type, inline, water-cooled engines, for example the Rolls-Royce Merlin and Griffon engines. The epicyclic reduction gear layout is quite compact and has the advantage of being a concentric layout. All of the gears rotate about the same center line. The gears themselves may be straight cut, beveled, or even helically cut. Helically cut gears are extremely efficient in the way they transfer power, and they are also very smooth and quiet in operation. They do, however, impart a degree of end thrust which has to be contained, usually through the use of thrust bearings. This end or axial thrust is proportional to the torque passing through the shaft of the gear. Axial thrust, as we'll shortly see, can be used to provide a torque indication system in a propeller reduction system. A torque meter can be provided to give the pilot information about the amount of power the aircraft engines are generating during any phase of flight. The instrument may be calibrated in units such as pounds per square inch, pounds-feet, Newton meters, brake horsepower, or any other suitable unit of power. Either electronic or hydraulic torque meter systems can be found in service. An electronic torque meter system, such as the one shown here, utilizes the angular displacement of a drive shaft, which is placed between the engine and the propeller drive. This displacement, being proportional to the transmitted power, is measured electronically, and the signal thus generated is used to drive the needle in the torque meter. This system is inherently lighter and more reliable than the hydraulic system. There are two types of hydraulic torque meter system, one which utilizes the end thrust generated by a helically cut gear, the other employs the torque reaction of a ring gear. They are both used to alter the oil pressure of the torque transmission system, which is then transmitted to the torque meter gauge on the instrument panel. This simplified diagram shows a ring gear system. When the engine is running, the pinions or planet gears are being driven around inside the stationary gear by the central engine crankshaft. The thrust reaction generated by the rotation of the pinions will try to rotate the stationary gear in the opposite direction to that of the pinions. The stationary gear is restrained by being attached to pistons fitted within cylinders that are being supplied by oil pressure, which is generated by a torque meter system pump. One of the pistons in the system partially covers a bleed hole, which, if it's uncovered, will allow oil pressure to be dumped to the engine oil return. While the engine is running, the piston in the cylinder with the bleed orifice will take up a sensitive position where the oil pressure generated by the torque meter pump just balances the thrust being generated on the stationary gear. If the engine torque increases, the piston will be driven, by rotation of the stationary ring gear, to cover more of the bleed hole. This will cause the oil pressure within the cylinders to increase until the piston moves back into the sensitive position, where torque meter oil pressure once again balances engine torque. The increase in oil pressure required to achieve this balance is indicated on the torque meter gauge as a rise in engine output torque. If engine torque decreases, the oil pressure in the cylinders will now exceed the pressure required to balance the torque output of the engine, which is acting on the stationary ring gear. As a consequence, the pistons, which were being maintained in a sensitive position by the balance between the engine torque and oil pressure, will now move to uncover more of the bleed hole. This will cause the oil pressure to decrease until the piston moves back into the sensitive position, where torque meter oil pressure once again balances engine torque. The decrease in oil pressure required to achieve this balance is indicated on the torque meter gauge as a fall in engine output torque. Engine torque is proportional to the horsepower being produced by the engine, and this is transmitted through the propeller reduction gear. The helical gear torque meter system depends upon the axial thrust which is developed when helically cut gears are used to transmit power through the propeller reduction gear. The shafts of the gears rotate within cylinders, and the axial thrust they develop is balanced by oil pressure trapped inside the cylinders. Torque meter oil pressure is transmitted to a gauge in the cockpit. The gauge is calibrated in pounds per square inch. The system oil pressure, which in some systems can have quite a high value, for instance the Proteus engine was capable of developing about 800 pounds of torque, is generated by a torque meter system oil pump. In this system, which is similar to that used on the Rolls-Royce Dart engine, there is an oil pressure bleed hole within each cylinder. When the thrust developed by the helically cut gear is exactly balanced by torque meter oil pressure, the shaft of each helical gear takes up a sensitive position, partially covering the bleed hole. If engine power output increases, the axial thrust being transmitted by each gear also increases, which forces its shaft further into its retaining cylinder. Thus the shaft is forced into a new position where it blocks the bleed hole. The torque meter oil pressure, being unable to escape, now builds up to a new higher value, until it's able to force the gear shaft back into the sensitive position, where once again it's able to balance the axial thrust being developed by the helical gear. If the engine power output decreases, the axial thrust being transmitted by each gear also decreases, which allows its shaft to be displaced slightly out of the retaining cylinder. Thus the shaft is forced into a new position where it uncovers the bleed hole. The torque meter oil pressure now falls to a new, lower value, until the lower axial thrust being developed by the engine is able to overcome it and force the gear shaft back into the sensitive position in the cylinder. Once this has happened, axial thrust is again balanced by oil pressure in the cylinder, but now it's balanced by a lower torque meter value. In addition to giving an indication of engine power output, the torque meter system can also be utilized to send signals to the auto feather and the water methanol injection systems. The auto feather system, as its name implies, will automatically feather the propeller of a failed engine. This is particularly important if the failure occurs on takeoff. The checks to be carried out on a propeller after engine start and the methods used will vary from aircraft type to aircraft type and from propeller type to propeller type. In addition to the checks which are described here, it must be remembered that there are many other checks which are carried out on propellers. Most of these checks are maintenance orientated, but nevertheless a pilot is still responsible for the pre-flight visual inspection of the propeller. The particular checks that we are about to examine are those for the single-acting propeller fitted to the Piper PA-34 200T Seneca aircraft. After engine start, the engine oil must be warmed up to the level required by the operating manual before any checks are commenced. The checks form part of the normal after start and before takeoff checks. For the sake of minimizing confusion between gauges, we, in this demonstration, will concentrate only on the left or number 1 engine. The first check is a part of the power check. The remainder forms part of the before takeoff check. Here we've highlighted the particular parts of the checklist that we are concerned with. Throttle, 1900 RPM. Be aware that you don't really want to use any more RPM than necessary. Propeller, RPM lever. Exercise. This part of the check ensures that the propeller functions correctly under the impetus of the oil pressure being fed to the pitch control mechanism. Check. RPM drops when min RPM selected. Check. RPM drops when min RPM selected. Pull the propeller control lever to minimum and allow the RPM to decrease by 200. At this point, it's not necessary to wait until the RPM falls to the absolute lowest possible value. You're only checking for the correct functioning of the propeller control system. Check. RPM returns to 1900 when max RPM selected. Return the propeller control lever to maximum RPM and check that the RPM recovers back to 1900 as the propeller blades move back towards fine pitch. Repeat. Repeat the previous 2 checks again. By doing this, you'll ensure that warmer oil is being introduced into the propeller control mechanism and the associated pipework. The warmer oil will sharpen up the propeller's response to your movement of the propeller control lever. Throttle, 1500 RPM. Moving the propeller control lever back towards the white line on the control quadrant with this power set should not elicit any RPM change at all, because the propeller is within the constant speed range. Propeller feathering. Check. Moving the propeller control lever below the white line will cause the propeller blades to move towards the feathered position and the RPM to decrease. If, as is the case with the propeller we are considering, a centrifugal latch mechanism is fitted, it's important that the RPM should not drop below 1000, because the centrifugal latches will not become engaged and the propeller will feather, which is not what we're trying to achieve in this check. Throttle. Close and set 1200 RPM. Initially the throttle lever should be closed and the slow running RPM checked at between 7 to 800 RPM. Then the throttle should be set to obtain 1200 RPM. At this RPM the engine should run smoothly and the spark plug should not oil up while you're carrying out the checks on the other engine. Propellers. Max RPM. Select the propeller control lever to the maximum RPM position. Propeller de-icing. As required. If icing conditions expected during or immediately after takeoff, select On. Check propeller de-icing ammeter. Check both alternator ammeters. If your aircraft has double-acting propellers fitted, then the checks to be carried out are much the same as those for an aircraft fitted with single-acting propellers. There will, of course, be differences in detail concerning the basic RPM settings, etc., but the object of the checks will be the same, that is, to ensure a rapid and accurate response to RPM control lever movement. As with the single-acting propeller, it's necessary, once the lubricating oil in the engine has warmed sufficiently, to exercise the pitch change mechanism. This will evacuate the cold, sluggish oil from the pitch change cylinder and purge it from the constant speed unit and the associated oil passages. Just as happened with the Seneca checks, once the oil temperature is increased, there will be an engine test procedure for the double-acting propeller, which will involve causing the pitch change piston to travel from the fine pitch stop to the feathering stop more than once. With a double-acting propeller, there is not only double the amount of actuating oil in circulation, but also an extra system to check. The correct performance of the feathering pump will have to be ascertained, along with the functioning of the pressure-operated cutout switch. This concludes the lesson on propellers.